And we're back and better than ever, still in 18-2, where we're dealing with reversible reactions and equilibrium. In the first podcast, we took a look at what a reversible reaction is, one in which both the forward reaction and the reverse reaction will occur at the same time. And we also introduced you to the idea of chemical equilibrium, where the reaction appears to be stopped, but yet there's still an intermixing of the particles. They are still shifting back and forth. It's just you can't see an overall change. And we were wrapping up with our discussion where we're trying to illustrate what this dynamic equilibrium meant. All right, so let's go ahead and scroll down here, and maybe we can illustrate this a little bit better. Again, let's say we're dealing with people that are going home. This will be their home. And we have people that are going to work. So this will be the factory. Okay, and let's say at any given point you have 100 people at the factory and you have another 100 people at home. And so what will happen is that throughout the day you will have certain people coming into work and certain people going back home. So at any given point you always have 100 people in the factory working, and you always have 100 people who are either on their way home or at home. And so if you took a look at the individuals, you would know that they are different workers at one point or another. The individuals do in fact change, but if you're simply looking at the numbers don't change. Well, when you're dealing with a factory, of course, people know each other's faces, they know each other's names, etc. And so you can tell that there's a change going on. However, molecules aren't like that. They're all identical to one another. So you can't tell one molecule to another. Well, there are ways that you can do this. But overall, there's not much way to tell a difference between individual molecules. And so when equilibrium occurs, all you see is a certain number of molecules on the reactant side, a certain number of molecules on the product side, and there is no change in those numbers, and so then you are at equilibrium. Now, where does this equilibrium occur? Well, it's actually different for different reactions. Some reactions, now we're looking at down here, some reactions will lie predominantly on the reactant side. Simply meaning this: if we have calcium carbonate will naturally decompose to calcium. I'm going to fill this in just a second. Calcium oxide and carbon dioxide gas. But this only happens to a very, very small extent. So if I was going to draw in some arrows, I would say that most of the arrow is pointing back to the reactant side, and only just a little bit of it will go to the product side. And so this reaction is said to lie far to the left. Most of the reaction is on the on the reactant side. So if I did this generically, I would say A and B are in equilibrium with one another, and now I'm using two arrows that are equal size, but at equilibrium 99% of the molecules might be A when only 1% of the molecules would be B. So very little of it goes to the right. Most of it stays on the left. On the flip side of that, you have reactions that do the opposite, where if you have A in equilibrium with B, 99% of it might be on the product side while only 1% of it is on the reactant side. So most of the reaction goes to the right, so we say that this reaction lies far to the right. A good example of this would be taking silver ions in solution and chloride ions in solution. Most of those are going to turn into silver chloride solid. But a very, very few number of particles will go back to silver and chloride ions. So that's what equilibrium looks like. It's different for every reaction, and so you have to have a way of expressing what that is. Now, equilibrium can be shifted back and forth. And that's the next topic. It's called Le Chatelier's principle. Le Chatelier's principle will tell you whether or not a reaction is going to be moving to the right or to the left. And all the principle states is that if a stress is applied to a system in dynamic equilibrium, the system changes in a way that minimizes or relieves the stress. Now, that seems like a mouthful. It is actually quite simple. Let's take a look at a system that's in equilibrium, A and B going to C and D. If you add A or B, how is this thing going to respond? Well, it wants to minimize this addition. So if you add something, it's got to shift away from it to remove. It'll turn some of the A and B into C and D to minimize this addition. So this will shift equilibrium. That's what my little symbol for equilibrium, the two little squiggle lines there. It's going to shift equilibrium to the right to minimize the addition. On the flip side of that, you could add C or D. If you add C or D, it's got to remove those by reacting them to form A and B and shift equilibrium to the left. So if you add anything, the reaction is going to move away from it. All right. On the other hand, you could add something. You could remove something. If you remove A or B, in order to minimize that effect, you have to fill it back up. Well, how do you fill it back up? You have to shift this equilibrium to the left, or draw it to the left. Draw equilibrium to the left. On the other hand, if you remove C or D, it's going to try to replace it. Well, how do you replace C or D? It's going to draw the reaction towards it to fill in that void. So it'll draw the equilibrium to the right. All right, so Le Chatelier's principle, though, and I'm not going to ask you to write out that definition, it is simply this. If you add something, it's got to shift away from it. If you remove something, it's got to try to fill it. We will do a demonstration about this in class using cobalt chloride. It's a brilliant equilibrium that shifts between a nice pink color and a navy blue color. We will also take a look at this in class using a demonstration of a dark brown NO2 gas in a colorless N2O4 gas. Alright, so we'll leave those blank for right now, but we'll take a look at those in class. We'll see you next time.